Extinction risk is one of the key things that conservation biology is focused on reducing. There's another concept called expected minimum population size, which might be a little bit more useful when ranking management options. For a very simple stochastic model where we have random births and deaths, and there's a probability B of a birth and a probability D of a death, we looked at this simple model in Chapter 5, you can calculate the probability of persistence over any finite amount of time given the initial population size. It is a very simple expression. It's just 1 minus the death rate over the birth rate raised to the power n naught. So as n naught gets larger and larger, this probability of persistence, this term here, this term gets smaller and smaller, and the probability of persistence gets closer and closer to 1. But it's never going to get entirely to 1. Let's take a look at the probabilities of births and deaths. If the probability of death is less than the probability of birth, then this thing here is going to be less than 1, and that means we're always going to have a possibility of persisting, even if n naught is very small. However, as long as the birth rate is bigger than the death rate, then the probability of our average population growth rate is going to be positive, but there's still a probability that it's going to that the population will not persist. The only way that it could fail to, or it will have a guaranteed way of persisting, is if D is 0. If D is 0, then this thing is 0, then it doesn't matter. But no death rate is a completely unrealistic perspective. So the probability of persistence gets higher as the population size goes up, and higher as the birth rate gets larger than the death rate. If the birth rate and the death rate are equal, then this thing is equal to 1, and the probability of persistence is 0. So that's quite an important boundary. So if our probability of persistence is, if the death rate and birth rate are equal, or indeed even if the death rate is bigger than the birth rate, then you're going to find that the probability of persistence is 0. That's what we would call a driven extinction. It's a population that is headed deterministically towards going extinct. But what this expression also tells us is that if B is bigger than D, that is, on average the population is going to grow, there's still a probability that that population will fail to persist. If we graph that thing out, you can sort of see what it looks like. If we look very closely at very small population sizes, so 0 to 50, we can see that the probability of persistence rises quite quickly and then is almost virtually 1, or indistinguishable from 1. And if we look at a larger time scale down here, we can see that it's also pretty much 1 across that area. This dashed line here, though, so this top line assumes there's no catastrophe. So the only stochasticity we've got is just random births and deaths. So once our population is reasonably large, there's a very good probability of persistence. However, the picture changes dramatically if we include catastrophic effects. So this is a large, not very common, but large declines in population size. And in the presence of catastrophes, now the probability of persistence drops quite a lot. So catastrophes are really important for figuring out what the probability of persistence actually is, because ignoring catastrophes tends to overestimate the probability of persistence. Another way in which people look at these concepts is to calculate what's called quasi-extinction risk. So this is a logistic model that's experiencing demographic stochasticity, so random births and deaths. And the carrying capacity is 100. And on average, over time, the population is going to increase. But there's a lot of wobbling up and down. So there's quite a few populations that that get very small. In fact, there's several of these traces that actually intersect the zero line, that is, they go extinct, and there's quite a few that go well up above it. And so what we try to do is we'll often choose a time point, say 50 years, and we'll summarize what that population distribution looks like as a cumulative frequency curve. So what this cumulative frequency curve, you can imagine, it's a bit like a histogram where each of the bars has been stacked up on each other until we get all of the bars stacked up here. So the way we can read this thing is we can look along here and say, okay, 100, about 75% of the populations at time 50 have population sizes less than 100 individuals. And if we go a bit farther, all of the population, all of the replicate populations have population sizes less than 200. So this thing here is called a quasi-extinction risk curve. So we can choose any point along that and say, let's say 50, right? That's the point at which we're starting to see very strong effects from genetics, and so our model here doesn't include any genetics, so we might say, well, we're really worried about what's the possibility, not of getting to 0, because we can't estimate that very well, but rather the possibility of getting a population size as small as 50. And in that case, we can see that, you know, the quasi-extinction risk here is about, what, 0.2, something along those lines. So that means this population has a probability of 0.2 of dropping to a population size of 50 or lower before at time 50. If we increase little r for this population, this thing rises up to a higher level, and that entire quasi-extinction risk curve, that entire population distribution shifts over to the right. So this represents a decrease in risk, so an improvement in the population parameters. A higher value of little r gives us a quasi-extinction risk curve that's farther over to the right. Similarly, if we were to include catastrophes, this curve would shift over to the left. Just like before, the probability of persistence gets lower if we include catastrophes. This model is not including catastrophes, so that would shift that entire quasi-extinction risk curve over to the left if we were to include catastrophes. Another way of thinking about a population, which is actually perhaps a little more, is thought to be a bit more sensitive than quasi-extinction risk, and also has the advantage of not being tied to a particular time point in the future, is to calculate the expected minimum population size. So for each of our replicate runs here, where this population is or each replicated random population is wobbling around, we can ask, what was the smallest population size that it ever observed? So for some of those, that might have been the initial population size, but for others, it occurred at some time later and perhaps at a much lower population. The ones that are along the x-axis here are the ones, of course, where they went extinct. Those points are so these points here show for an individual run, where did the minimum population size occur, and the expected minimum is then just the average of those points, and it gives us a sense of what is the sort of worst case scenario that's likely to happen, that's expected to happen over all of the different replicated runs. And here's what happens if you crank up r, little r, population rises up better. It still has a broad range of expected minimum population sizes.